All right, so 2 weeks ago we solved a problem involving this Atwood machine and two masses, one heavier than the other, starting a distance h off the ground, and we solved it with dynamics. And then last week we solved it with energy, the same problem, and we found the max height that the little block ends up off the ground. We found that to be 1.46 meters. Because not only does the little block get lifted up the same amount h off the ground that the big block falls, it then ends with some final velocity and scrunches the rope and becomes a little projectile that goes up an extra, I think it turned out to be 0.26 meters. Well, today I would like to make this, add on to this problem even more once again, and say, what if the pulley had mass? So before it was a massless pulley. What if the pulley had mass? So let's say it has mass little m, which was 2 kilograms from the previous problem. And let's say we wanted the little m mass block to end up at the same height, 1.46 meters. In this case, what must the big M block mass be to achieve this? So the previous M, I'll say previous, was 5 kilograms. And so just thinking about this, playing it out in our head, now that the pulley has some mass, it's going to take something, to rotate that pulley. And so the big M block must need to weigh more than 5 kilograms to get that little m block up off the ground the same amount. It must be heavier. So we're going to expect an answer of greater than 5 kilograms, but not sure by how much. It's kind of an interesting problem. So we're going to do this with dynamics just to show that method. We'll do it with dynamics. Not sure if I will then solve it with energy after. Maybe that'll be the following week, or maybe this problem starts to get boring. So let's see. Free body diagram for the little mass. It's going to look the same. We have little m, g down. We have, so now with the pulley having mass, we have to realize that there's two different tensions in the two different sections of the rope here. So for little m, I've just labeled this T2, so I'll stick with that. And it is moving upwards, so acceleration upwards. And so I'm going to take my positive y in the upwards direction. Right. Then we have, I'll just go around the clock here. So pulley. So the way that we model a pulley is we allow the forces to act as they do because it is going to be rotating. So we have to consider some angular dynamics here. So this has a radius that we can just kind of say r. It turns out these radii always end up canceling out, but we got to have something to place in there in order to get there, I guess. So we have a T2 pulling down on that side, and also a distance of the radius away from this center axis. We have T1 pulling down on that side. There's also mg here, and that's counteracted by, I don't know, maybe we can call this T3. But we also know that it doesn't go anywhere, it doesn't translate anywhere, through X, Y, Z space. And so those are kind of unnecessary. We know that it's going to have some torque applied to it. It's going to rotate, and T3 is just equal to the weight. It's just hanging there. But I guess we throw those in there too, why not? And when we are considering something that's rotating and the forces that are acting as they, where they actually do, I like to take a coordinate system that is kind of outside the whole thing and say this. And what we know is it's going to be rotating like this. That's the acceleration, angular acceleration, alpha. And so I'll go ahead and say that my positive rotational axis is in the direction of the angular acceleration. All right, continuing on, now we have big M. And we did this one just before. So, boom, boom, and then T1. And we have acceleration downwards. And so we're going to take, we're going to take down to be our positive y-axis. And there's our free body diagrams, our 3 free body diagrams. All right, so now we're going to sum some forces. So for the little m, I'll just do it directly below. We're going to really care about one equation for each. The sum of the forces in the y for the 2 blocks, and the sum of torques for the pulley. The sum of forces in the x don't exist for any of them. There's no x component forces, and the sum of forces in the y for the pulley, we said it's not going to translate anywhere. That's not going to get us any information. So there's just going to be one equation underneath each of these. So sum of the forces in the y here. We have T2 minus mg equals ma. Sum of forces, sum of torques on the pulley, so this will be about the center of mass, is equal to, let's see, we have, and making it rotate in the positive direction, we have RT1. For pulleys, so this is R cross F, so for pulleys, it's always going to act at that 90-degree angle. So sine of the angle between R and T is 90, and so sine of 90 is 1, so it just simplifies to RT, which is really nice for pulleys, minus RT2 for the torque counteracting that, and that's going to be equal to I alpha. Now this I here, we can model a pulley as a solid cylinder, which has moment of inertia of 1/2 mr squared, right? So it has some radius r, it has some stated mass, lowercase m, and then alpha is equal to a over r. So we're going to have all of our r's end up canceling. So let's go ahead and rewrite this equation below. So if you see, all the r's are going to cancel. So we're going to have T1 minus T2 being equal to 1/2 ma. Nice and simple. And then for this final equation over for this big M, which I've kind of scrunched into, sum of the forces in the y, we have acceleration down, so we have big M g minus T1 equals big M a. So here we have some equations. So this looks great for being able to plug in T2 and T1. And then we can solve for an A, and maybe that gets us somewhere. Ultimately, we have a constant acceleration problem to solve, but I think ultimately we will want something. Oh, we won't be solving for A. In fact, we want to know what the big M is. So we want big M, which exists over here. But T1 needs to be plugged into there, and it contains a T2, so we're going to be doing that type of a thing. All right. So let's see. I'm going to solve it the way that I was intending originally, and then we'll get all of our M's together. So this is T2 is equal to MA plus MG. It's just too tempting. These tensions are just sitting there waiting to be solved for this. MG minus MA. Then we can just plug it into this middle equation here. So we have mg minus ma, that's T1, minus, we'll have to remember to apply this minus sign to both terms, so minus minus equals 1/2 little m times a. That's not too bad, right? All right, even though we're focusing on big M, my mind kind of just always solves it that way because it's almost always acceleration and the tensions are just right there. So now we want to get big M on one side and everything else on the other. So big M G minus A equals, let's see, 1/2 MA plus MA. Oh boy, so that's going to be 3/2 MA. 3/2 MA minus, nope, send it over the other side, it becomes plus MG. Okay, so big M then is equal to, let's see, we can pull out an M, I guess. I don't know if that makes it any easier, but we can do 3M over, no, we don't want to do that. We can pull out an M, and we do 3A over 2 plus G divided by G, what am I doing? Divided by G minus A. All right, I think that's as good as we can get. It doesn't really look too great, but I think that's as good as we can get. So here's our M, right? So this is where we apply this problem-solving kind of thought of, look at all this stuff that we do know, right? We know G and everything, right? And if we just knew A, which shows up in two different places, if we just knew A, then we'd be done with this problem. So we need A. We need A. So that's ready to go, but we need A from some other way. So we gotta go back and find another method for this. In other words, we have one equation with two unknowns, yeah? So more information that we know the final height is 1.46, right? And we know that this really comes in two stages. There's the stage where the big block is falling and there's like tension pulling the little block up. And then there's the next stage where there's just gravity as an acceleration and pulling it down, right? So, and the total height that the little m reaches at the end of that is 1.46 meters, starting 0.6 meters off the ground, right? So this is kind of like a double segment constant acceleration problem. This is what I'm going to say. So it starts here and it goes up a distance h, and then it goes up another little bit to a final height of 1.46 meters. So here I'm going to do that. I'm going to split it in half, even though one's longer than the other. And I'm going to say that this here, so we'll do y's. Y naught is 0.600 meters. V naught is 0 meters per second. T1 is, I don't know. A1 is what I really would love to be able to plug in over there. Y1 here. So this is just that first segment. So that is when the big block is falling from a height h down to the ground. And so the little block is going to raise by the same amount, h, right? So this is going to be h. I'll just put h there, or maybe I'll put it's going to be 2h if it's starting, why not, h off the ground. So this is going to be 2h. So 1.20 meters, right? Okay, and V1, I don't think we know V1, right? We don't know V1. And the last problem, that was what we were concerned with entirely, but right now I'm not even sure we need to know V1. Then there's going to be a time t2 for the second segment, a2. So in the second segment, the rope is scrunching and the acceleration is just minus g, gravity pulling it downwards, because this is like the positive y-axis. And then y2, this is what we do have information about. It is 1.46 meters. And v2, what is v2? Well, when it reaches a maximum height, that's 0 meters per second. So it's no longer traveling upwards at all, right? All right, so we have quite a bit of information. For this first segment, we want to ultimately know A, because that's what we can plug in over here, right? And then we have our answer. So that's what we're really wanting to get to. The times, we don't necessarily need to know. And V1, we don't need to know, but any which way, stepping stones to get to that A1 would be great. So first segment, we have 3 unknowns, and we cannot solve for A1 directly. So we got to jump over to the second segment and take our information from there. So we have an unknown of V1 and an unknown of T2. And the one that links this first segment to the second segment is V1. That would be nice to know, because if we can solve V1, then we have one less unknown for segment 1, and we can do a don't know nor care about T1 and solve for A. So let's go ahead and do that. So we want V1, and we don't know nor care about T2. Looking at the second segment here, don't know nor care about T2. So we need to use that constant acceleration equation here that does not contain T. So applied to the second segment, V2 squared equals V1 squared plus 2A2, and then the displacement, Y2 minus Y1. So V2 is 0. V1 we want to know. A2 is going to be minus G, right? And the displacement here, the displacement is 0.26, just looking at Y2 minus Y1. So V1 is equal to the square root, yeah? Or maybe we just leave it squared, since, we'll probably use the same equation next. We won't know nor care about T, so we're going to have to plug it in for V squared. So we'll just leave it here. V1 squared is equal to 2G times that 0.26, right? 0.26. So really like 0.433, repeating maybe, G. That's what I get. No, that's not what I get. I was looking at my paper and my eyes were jumping ahead. We're just going to leave it as, let's see, 0.52 G. That's what that would be, 0.52 G. All right, now 0.52 times G. Now we get to plug that in using an equation, same equation for this first segment. We want to solve for A. We don't know nor care about time, so we use the same equation, but with the first segment. So V1 squared equals V0 squared, which is 0, plus 2A1 times Y1 minus Y0. All right. So V1 squared is exactly what we just had. So 0.52 G is equal to 2 times A1, that's what we want, times, what is this? y1 minus y2, that's h, or 0.600, right? And if we're multiplying that by 2, then that's going to be 1.20 times a1. And so therefore, if you divide that over, then you ought to get a1 equals 0.433 G. All right. So that's our A, and we can go and we can take that and plug it in for both places over here, right? Plug it in for both places over here. So 0.433 G. So we have big M being equal to little m times 3 halves. Let's see, I'll do it this way. 3 halves times our A, which is 0.433 times G, right? Or I'll do the parentheses outside because that's all the one thing. Then we have plus G, a lot of G's showing up, right? Divided by G minus 0.433 G. Awful lot of G's here, so all the G's go away. We can pull a G out of the top and the bottom, so I'm just going to do this, right? And so then what you end up actually getting, this little m, is 2 kilograms, right? So what you end up getting is 1.65 times little m divided by 1 minus 0.433 is 0.567. And since little m is 2 kilograms, then you get 5.82 kilograms if you plug it all in for big M, which, if you'll remember, is larger than 5 kilograms. And it's just a little bit larger, which makes a lot of sense, or it gives me a lot of confidence that we did that right, because we just took the pulley and we gave it 2 kilograms of mass, right? And so that big M needs to be just, 0.82 kilograms heavier to make the same thing happen, but now we're not ignoring the fact that the pulley has mass. So that's kind of neat. Just a little bit of more realism to the problem here. All right, and if I'm not bored by this problem yet, then maybe you can guess the following week might be doing this with energy. We will see, or maybe I move on. All right, let me know if you like these, and drop a comment if you have a problem that you'd like me to solve. Have a great day.